Coordination compounds will exhibit magnetic properties. Magnetic properties are those properties that the compounds are going to exhibit when they are exposed to an external magnetic field. These magnetic properties are going to be determined by the splitting of the d orbitals. The electron configuration that you're going to have for those electrons in the d orbitals of the metal ion, right, are going to depend on how large or small is that splitting between your d orbitals. The complexes can be paramagnetic or diamagnetic. This is how they're going to exhibit different magnetic properties. When you have paramagnetic complexes, those complexes are going to have unpaired electrons in those orbitals. If they do have unpaired electrons, they will feel a strong attraction for a magnetic field. For diamagnetic compounds or diamagnetic complex ions, the diamagnetic, they won't have any unpaired electrons. All of the electrons are going to be paired in the d orbitals. Since the electrons are paired, they will feel a weak attraction for a magnetic field. Now your complexes as para or diamagnetic, that's going to depend on the splitting of the orbitals and also the total number of electrons. Let's review Hund's rule because your electrons are going to be placed in the orbitals following this rule. So for Hund's rule, what we have is that when you have your electrons and you're placing the electrons in your orbitals, right? If the orbitals have the same energy, which means that they're degenerate, your electrons are going to occupy the orbital single first. So one electron at a time until you don't have more orbitals with the same energy, and then the electrons are going to start pairing up. So you have your d orbitals, they're splitted, right? You have 3 d orbitals at a lower energy level with the same energy. These 3 right here. And then you have 2 above, okay, with the same energy. So if you have just 3 electrons to place in those orbitals, the 3 electrons, you have 3 orbitals on a lower, right here. So your 3 electrons will be placed 1 in each one because you have 3 empty ones. So there's no need to pair the electrons at all. That's following Hund's rule. Now, when you have 4 or more electrons, you can have cases where that 4th electrons will be paired on the low energy level orbitals, the green ones, or you will have cases where that 4th electron will go on the orbitals that you have above. That's going to depend on the splitting. So I'm writing here the spectrochemical series listing all of your ligands. So you have the strong field ligands on the left, weak field ligands on the right. They're separated by a color. So you have the blue ones for the strong, and then you have the purple ones for the weak field ligands. Strong field ligands will always give you a large splitting. Weak field ligands will give you a small splitting. When you have strong field ligands with that large splitting between your d orbitals, they will form what is known as low spin complexes. When you have weak field ligands, the ones that are giving you the small splitting between your d orbitals, they will form high spin complexes. Now, when you have electrons in your d orbitals, right? You can have from 1 electron all the way to 10 electrons. If the number of electrons in your d orbitals is 1, 2, or 3, okay, there's no difference between low spin or high spin. 1, 2, or 3 electrons can go on the 3 orbitals that you have on the bottom part. What's going to make your complex be high spin or low spin, it's when you have 4 or more electrons in the d orbitals. So what I have here is like a definition or a simple explanation to what's happening with low spin and high spin. So for low spin complexes are those that you're getting when you have strong field ligands bonded to the metal. For those low spin complexes, it takes more energy to occupy the higher energy level, the two orbitals that I have highlighted in yellow, than the amount of energy that is required to pair the electrons on the 3d orbitals that I have highlighted in green. That's how you get a low spin complex. For a high spin complex, the amount of energy that is required to pair the electrons, right, it's higher than the amount of energy that is needed to occupy that higher energy level that I have highlighted in yellow. So let's look at this with an example so we can check the ligand, how many electrons we have in the d orbitals. So now we are combining, finding the oxidation state for the metal, finding the electron configuration so we can determine how many how many electrons in the d orbitals we have, so we can determine if it's a high spin or a low spin complex. So we can ask the same information in different ways. So I have examples for all of them. I can ask you to find out the number of unpaired electrons. But to find out the number of unpaired electrons, you still have to check if it's low spin, high spin. You still need to look at if it's paramagnetic or diamagnetic. So all of these questions are related because you're actually checking everything in order to answer them. So I'm going to start by checking my complex. I have a complex containing iron, that's the metal. It's a complex ion, and your ligand is Cn. Okay, so Cn, it's in your list, and that's a strong field ligand. So we have identified that ligand as a strong field ligand. Now we need to look at the metal. If you're good with the electron configuration, so you don't have to write down the electron configuration for iron, the metal, not the ion. But if you're still practicing, you should write down both electron configurations. So I have my electron configuration for iron iron 0, no charge, will be argon for S2, 3d6. That's 26 electrons right there. Now we need to find out the oxidation number for the ion of iron in my specific example. So you have 6 ligands Cn. Cn has a charge of -1, so that will give you 6 times -1, which is -6. X is just the charge of the metal that you're trying to calculate. When you add all of the oxidation states, that will give you -4, which is the overall charge of the complex ion. So solving this will give you that the value for X is +2, which means that's your oxidation state for the ion of iron in that complex ion. So if your oxidation state is +2, it means that that ion is losing 2 electrons, and for your transition metals, they're losing electrons first, right, in the 4s orbitals for the transition metals that you have in the 4th energy level, which means that for Fe plus 2, you have 3d6, right? It's argon 3d6. No electrons in that s orbital in the 4th energy level. So you have 6 electrons in the d orbitals. That's why we're doing this, to determine how many electrons you have in the d orbitals. Now, the question is asking you how many of those electrons are unpaired, which we can use to find out if it's diamagnetic or paramagnetic. So to find out how many, like you might think, okay, if it's D6, that's a even number, so all of my electrons are going to be paired, but that's not the case. Remember, you have your orbitals, the orbitals, they're splitted, and they're going to occupy, the electrons are going to occupy those orbitals following Hund's rule. So your Cn, which is a strong field ligand, it's a low spin. So I have my 6 electrons in the d orbitals, right? I have my 5 d orbitals here represented with showing the splitting between them. If this is a low spin complex, because you have a strong field ligand, we're looking at this part right here. It's telling you that it takes more energy to occupy the 2 orbitals that you have up here. So I'm going to start placing my electrons. It's 6 of them, right? We always start placing electrons in the lower energy level. So we have these 3d orbitals at a lower energy, these ones right here, and then we have the 2 up here. So my electrons, I'm using 1, 2, and 3. Okay. I have 3 available orbitals, so I'm placing 3 electrons single first, following Hund's rule. But now I still have to go all the way to 6. What's happening here now with the 4th electrons? Since this is a low spin means that you're going to fill the lower energy level orbitals first. That's low spin. So my 4th electron, since this is a low spin complex, it will actually go here, the fifth and the sixth. Okay. So if it's a low spin complex, you're going to use all of the three orbitals that you have on the bottom part first before you can actually move to use the two orbitals that you have above them. So here we have some other problems. So you can be asked to find out how many electrons are unpaired, or if you have any unpaired electrons in a specific complex. You can be asked to find out if your complex is going to have low spin or high spin, or you can be asked to identify a complex as paramagnetic or diamagnetic. So I'm going to solve one for each one of these, and then you can solve the other one. For the first problem here, this is asking you if a compound or a complex ion is paramagnetic or diamagnetic, which means that you still have to find out how many electrons you have in the d orbitals, where are those electrons going to be placed, if it's a low spin or a high spin complex. So I'm going to do the first one, and then you can try to solve the second one. So first, cobalt in the periodic table, it's element number 27, which means that you have 27 electrons. This is a transition metal in the fourth period in your periodic table. So electron configuration for cobalt as it is, not the ion for cobalt, is going to be argon, 4s2, 3d7. That's 27 electrons right there. 18 for argon plus 2, 20 plus 7, 27. Now, we need to find out the oxidation state for that cobalt ion. So your ligand is fluoride, and you have 6 of them. So I'm going to start writing my equation. X for the metal plus 6 ligands, each one with a charge of -1. That's equal to -3. So you can solve for X, and that will give you a +3. So that will be the oxidation state for the cobalt in the complex ion. So +3 means that that cobalt ion has a charge of +3. So you don't have 27 electrons now. Okay, 27 is for the element with all the electrons. So for cobalt to have that charge of +3, it's losing 3 electrons. It's losing the 2 electrons in the 4s first, and then another one from the d orbitals. So the electron configuration for that cobalt +3 is going to be argon 3d6. Okay. So you have 6 electrons in the d orbitals for cobalt +3. So let's write down our orbitals. It's always 3 on the bottom part and 2 above. Now our ligand for this complex is the fluoride ion, and fluoride is classified as a weak field ligand. So when you have weak field ligand, those are going to give you high spin complexes. So we have 6 electrons in the d orbitals. We have to place all of those 6 electrons in the 5 orbitals that we have available, always starting on the bottom part. So I'm going to start 1 electron at a time. So this will be 1, 2, 3. We have to go all the way to 6. So the 4th electron can be paired on the bottom part, or it can go on the 2 electrons that you have above. That's going to depend on which ligand you have and if it's a low spin or a high spin complex. Since the ligand that you have is F, and F is a weak field ligand. Weak field ligands will give you a small splitting, which means that you will have high spin complexes. Having high spin complexes means that that 4th electron will go on the orbitals that you have above. So I have 3 electrons placed, and this is a high spin, which means that after I'm done with the 3 orbitals that I have on the bottom part, I need to fill the ones that I have on the top part, high orbitals, so high spin. So 3, 4, 5, and we have to go all the way to 6. Now, we're following Hund's rule, placing 1 electron single first in each orbital. Since this is a high spin complex, we move from the bottom orbitals to the top ones. We have all 5 electrons, and now we have to place the 6th electron. Now the 6th electron, we go back because we have 1 electron in each orbital. So the 6th one, we have to pair that electron because you don't have any more orbitals available that are empty. So this will be my 6th electron right there. So the problem is asking you if it's paramagnetic or diamagnetic. For you to determine which one is, you have to actually look at the electrons. If you have unpaired electrons, that will be paramagnetic. So paramagnetic unpaired electrons, and in this example, you actually have 4 unpaired electrons. If the problem is asking you how many unpaired electrons you have, 1 unpaired electron, 2, 3, and 4. You have 4 unpaired electrons. Even if it's just one, that complex right there is going to be paramagnetic. If all the electrons are paired, then you will have a diamagnetic complex. So you have another one for you to work on, and I'm going to do the next one, letter A for the next one, and then you can do letter B. This one, this is asking you for how many unpaired electrons again. So I'm going to check my metal is still cobalt. You have the electron configuration for cobalt in the previous one. That's argon for S2, 3d7. Okay. But we need to check what's the charge for that metal ion right there. And cobalt is going to be +3. You can calculate, but you have 6 ligands. They're neutral, right? And your overall charge is +3. So that +3 will correspond to the charge of the metal. So your cobalt is +3, which means that you will have again 3d6. So I'm going to draw my orbitals 2, 3 on the bottom part, and I have to arrange my 6 electrons. But to arrange my electrons, I need to know if it's a low spin or a high spin complex. So let's check NH3. NH3, it's a strong field ligand. Strong field ligand means that you have low spin complexes. So you have to fill all of your orbitals, the bottom part first, because it's a low spin. So I have 6 electrons, 1, 2, 3. Since it's low spin, I need to fill all of the bottom orbitals first. So I have 3, 4, 5, and 6. 6 electrons, low spin. All of your electrons are paired. So how many unpaired electrons? That will be 0. Since this example here, you have all electrons as pair of electrons in your orbitals. This is an example of a diamagnetic. So you can solve letter B for both problems.